Good afternoon, everyone. Today we've got Prof Charles Okujeni, who is a Professor Emeritus of Exploration Geochemistry at the University of Western Cape. Prof Okujeni obtained his MSc and PhD degrees at the Technical University of Berlin in Germany in 76 and 80 respectively. He researched and lectured geochemistry at various universities across Africa for over 30 years. Furthermore, he served as the Association of Exploration Geochemists, that's the AAG, as regional counselor for Africa from 1995 to 2010. Now, I had the pleasure of meeting Prof at our Deposits of the Northern Cape event late last year, and he was telling me about some of the innovative techniques that is working with. And today he'll be talking to us on a case study on the use of geochemical and statistical data leveling techniques in enhancing element patterns for exploration terrains that are covered by regolith, including aeolian sand and calcrete. And with that, I will hand over to Prof, you may proceed. You may commence. Thank you.
Okay. All right. Thank you very much, Sufito, for the warm welcome, and thank you for having me. I'm going to talk about the use of geochemical data leveling techniques in prospecting transport-regolith dominated terrain, and this is more an area here in South Africa, in Southern Africa. I think exploration generally is moving, or has been moving, towards that direction, that new frontier, we'll call it. So I thought about giving this talk just to reinforce the importance of regolith mapping, in exploration, and also using techniques, which or data leveling techniques, which will allow us not to miss targets. I think that is something of interest, to anybody doing some work in exploration. Now, transported regoliths, depending on their provenance and their definition, aeolian sand, calcrete, stone lime, can promote or attenuate dispersion of elements, generally, or pathfinder elements. And the weakening of geochemical signature, I sort of define in terms of the coordinates X, Y, Z, that the elements, come from the subsurface, from bedrock and mineralization to the surface, and disperse X, Y, Z. And the weakening which takes place can be seen in terms of the amount of element that is being dispersed, mobile metal ions that are being, moved up, and also the composition of the regolith itself, which is more what is going to host the mineralization. So that composition can either weaken or it can enhance the dispersion. Right, so this is more in this framework, we are going to have that discussion. XYZ, composition, and composition of the fluids or the elements migrating up, and also that of the regolith components. Now, a lot has been done about partial leaches, MMI, which we use in the mining industry, but I always say that it also got its limitations. The limitations are that you actually get to leash what you have. So if you have a weaker anomaly, you are going to leash what is there. If you have a very strong anomaly, which I will show later, you're going to leash what is there as well. So I think when you begin to have this playing together, data leveling becomes very important. Now, the issues that we have today to discuss will be how can the spatial distribution of the regolith units and their geochemical controls be used to enhance interpretation of geochemical data, and also the migration pathway of pathfinder elements to the surface. The other question is, can a combination of regolith mapping and data leveling be used to enhance weak anomalies, and how? Now, definition-wise, data leveling is simply data transformation technique designed to maximize geochemical contrast in terrains with heterogeneous regolith units. And in this context, data leveling can be used in many other contexts, contextually used in many ways. You can use it even in the, when you have different analysis, different methods, different bedrocks, and so many other ways. But in this context, this is how I define it. Now, for you to do the data leveling for this context, this particular case, it's important that you should define the geochemical controls of the regolith units. That you must know the regolith composition and the interplay between them spatially. Second is that you should be able to select optimum data leveling transformation algorithm. So these are the things I'm going to talk about today. The first part of my talk is going to be on defining the geochemical controls and extent of regolith units. And the second part is selecting optimum data transformation algorithm. There are many data transformation algorithms, which I have listed here. I'm not going to go into all of them. Today, I'm going to use the Z-score power transform. The Z-score power transform has been used by many other authors, Stanley, 2005. So this is not really a new technique as such, but in terms of regolith, calcrete, aeolian sand, I think I have looked for literature I have not found. Here is Stanley's work. He fell on, like we all do, those of us in academia, we fall on old data, try to reinvent them and publish again. So Stanley did some work in 1984, and this is the anomaly pattern which he found. And then he did similar work again. I don't know if you can see this part of the screen because it's blocked in my view here. He did a similar work again in 2005, and he was able to actually see that there are patterns in the chalcopyrite zone. So in this zone, of course, in previous work, it was the anomalies or the patterns were rather weak. All right, so we come to the case study for today. I have chosen some old data, from a company. I have to say I decided deliberately not to put any coordinates or anything that has to do with measurement in terms of space in all the slides, just to safeguard. This work was actually based on some pre-work I did for the company, and they used it in that place to do the locality, to do the survey. So this is more like the palladium concentration, in profile traverses across. And we see the localities I've chosen 1 and 2. In locality 1, it's sort of very shallow transported regolith. In locality 2, the thickness actually increases. And we see the pronounced anomalies, in locality 1, and fairly faded anomalies in locality 2. On the screen on the right is the sampling that I did. So So this is the locality 1, the shallow transported regolith, and locality 2, the sort of deeper transported, regolith. This over 10 meters, this is about 2 meters, but that is excluding the saprolite. All right, the approach has been that we did sampling. I have talked about that, the localities. The samples were subjected to XRF analysis and graphite furnace, that's GSAS, graphite furnace AS. Deletion were done using hydroxylamine, hydrochloride, 0.05, 0.25, 0.05, 0.1 for the respective samples, subsurface and surface samples. The data evaluation technique is twofold, which I've actually said before. One is characterizing the regolith. If I have to use this to map in the field, what element ratios must I use to demarcate the regolith units? So that is all this first part. I used univariate statistics, cluster discriminant projection analysis, these are autodomain of immobile elements, and a bit of division of the regolith, all the regolith units considered, the upper part. So all this put together, I think you will see I've been able to come out with some element ratio which you can use to demarcate the calcrete from aeolian sand. This is followed by selection of the algorithm, which is the Z-power transform, which I've said, and at the end, I presented these in 3D maps. The first part really is just a bit of univariate statistics, box plots, which I've selected. So I'm not bringing out all the statistical parameters, but I just picked out the box plots, to just illustrate, the element patterns, which we have. I will start on the right. The right part of the screen actually shows, or the left rather, the left part of the screen shows all the regolith units that we have, in that area: aeolian sand, calcrete, saprock, stone line. Of course, the stone line comes after aeolian sand, followed by calcrete, and then saprock at the bottom. We see patterns here in terms of titanium, pronounced titanium in saprolite. The reason, of course, is titanium magnetite, mineralization. So certainly you should expect the high titanium there. Aluminium is higher in saprolite. That is expected because you have the alumosilicates, there. So one can actually begin to see, if you have the combination of regolith with the saprolite, in terms of aluminium, you should be able to discriminate, the two. Zirconium, that is now the upper part of the regolith, is a bit higher. It's higher in calcrete. I'm not able to see the other part of the screen, but I think I'll go to the other. Okay, here. The silica is higher in aeolian sand, which is acceptable. And important is that from that combination, one was able to look at the zirconium silica ratios. And on the right part of the screen here, we have the zirconium silica ratios. And in aeolian sand, it's less than in calcrete. And of course, the contrast here begins to tell me that you can use it to demarcate. Well, one would have thought that you just use calcium, but you can see the calcium values. They are quite, where to put the boundary will be quite difficult. You can only do this boundary here by using this zirconium. So we'll see that later. All right. So the box plots were more like speculation. It's when you really do the combination of cluster analysis and the discriminant projection analysis, you see the distribution of these elements in regolith. You can have a look at the standardized coefficients to verify what I have done. They are up here. I'm not going to dwell on them, but I rather want to focus on the diagram here, which is more the patterns, that I have tried to explain in the box plots become actually more evident, here. The domain diagram, which is coming from the discriminant display, this more like discriminant display projection, is that you begin to see that the entire regolith sequence, which is saprolite, stone line, calcrete, aeolian sand, is defined by negative Al2O3, positive SiO2, and negative Zr, and positive TiO2. So from those box plots which I showed, this is more like the summary of what is, whereby we begin to see that the calcrete is more defined by Zr. Okay, and variable in terms of alumina and silica. But generally, one can define the aeolian sand, stone line, and saprolite with Al2O3 and SiO2. Coming to the other diagram, the second one, which is to the right of the screen, this is more like the upper part of the regolith, which is where the prospection is done. And we see that the domain diagram is dominated by, on the left, on the y-axis by zirconium, and on the x-axis by silica. So silica and zirconium can actually distinguish aeolian sand from stone line and calcrete. Some bivariate plots, just to show that in the case of the silica, aluminum, titanium, zirconium plots, which is from that domain diagram, we sort of say the ratio of positive, negative, positive, negative from the two groups. You'll see more the sap rock at the bottom here, it's bluish, so a ratio somewhere around 5, silica aluminum ratio of about 5 could serve to remove sap rock. Whereas for the calcrete and aeolian sand, a ratio around 2. So around here, which is about 2.7. That ratio should be a way to demarcate, a point to demarcate between aeolian sand and calcrete. I have put this in sort of a prop plot, so that one can see here that boundary. Well, in the field, you all know very well, sometimes you have a mixture of things together. So there are some points that normally will fall out, but I've decided to present the data raw the way they are. Okay, so at the end, we can say we can demarcate aeolian sand from calcrete. We can also demarcate sap rock from the rest, as well. Now, just to give some explanation as to why zirconium is important there. Normally, with calcrete formation, there is ingress of solutions from from the bottom into the overlying regolith units. And in that process, there is some removal. Silica is removed out, and calcium carbonate, magnesium carbonate is formed. And that brings about retention of the high field strength elements and the large ion lithophile elements, and enrichment of also the middle rare earth elements and the heavy rare earth elements. So that is known. So zirconium belongs to these high field strength elements, of course, which this one can, oh, sorry, to go back. All right, so one part has been done, and that is we can demarcate regolith units. So when we outline the regolith units, we can then level the data because you have groups which you can consider separately, though the content in each group, and then level. Consider each group and see the potential, and then level the data. I have used just copper for this example. The raw data we have on the left, the level data we have on the right. So if you look at the histograms, the box plots actually show that as well. This seems to dominate here. It's a bit higher, the mean here. And bringing that, they are then leveled by the Z power transformation. Now, what that does is that it actually considers the samples, or the concentration of copper in the samples in the calcrete as a group, and then levels that to sort of get a group median value, or a group mean, and considered aeolian sand as a group, and levels these two means, or median values as the case may be. So that is what we have here. As a result, you have a shift. If you look at this and this, it's different, it's sort of a shift, which brings quite a lot of the copper content in the calcrete a bit to the right. I'm sure that's evident from the, and so you have a group representation, an equal group representation, so to say. Unlike when you are in the field and you just take the samples and you use a leveled or a uniform classification in identification of your anomalies. In this case, you are not. You are identifying, doing the anomaly estimation based on the group properties. And that is what is important, or the group element concentration in the groups. All right, so we now come to the 3D diagrams. I have leveled the copper, but before I show the 3D diagrams which are relevant, I just want to talk about why it is important to level data. What actually happens? This is a 0.25 hydroxylamine leach. It could be the same thing if you use data by XRF. In this area here, which is the locality 1, I said you have fairly thick, fairly thin regolith cover. And the layers I have put here, I have said before that I was not going to put any scale on anything and coordinate. So just, I don't know, I have to be careful. But the ore body is down here. These are the regolith layers, which you have. And that is the surface. And in the area we seeing regolith, right from the saprolite into the aeolian sand on the surface, I think one sees a continuous trend of element concentration around the ore. This is the ore body trend. So you see, and this is different as you go distal from ore, the concentration fades. So this is more like undisturbed, dispersion. I am sort of constrained by the number of data, drill hole points. I never had a lot of drill hole points, in locality 2, but just a few of them, which are available. It's just a projection. I've tilted the diagram a bit, so this is the surface. I know you were able to still see it. You can still see the trace, the drill hole traces here. And what we see is a sort of, now this layer here, the purple layer is more the calcrete, and we see attenuation of element dispersion towards the surface. So more like the calcrete is like a block, attenuating element dispersion or copper dispersion from the surface. Now, what do I see here? I do see that if you have dispersion towards the surface, it's going to be very sporous. It's not going to be uniform. It means when you sample the surface, here and there, you may actually get some anomalies, some weak, some very strong, but it's not going to be as uniform as you have towards the left here. And that is why the data leveling is actually important. All right, so here we have the level data. To the left, the copper values, well, I think I just need to explain this again. These are the layers, the regolith layers, modeled, and that is the surface here. I have put up here, hanging in the air, the surface sampling. It's just the projection so that one can see that is the sampling on the surface. And these are the horizontal surface sampling. I have discussed this before. This is what is in question, now. So the copper anomalies here were actually evaluated based on the copper concentration in the locality, in the traverses. That means if you look at just those traverses alone and do a sort of a quartile grouping of the copper concentration, you come to this. And again, we see right from the ore body here, you begin to see anomalous values trailing, to the left. When the data are leveled, when all the data are put together, which is now the two localities put together, then you have, less of those anomalies because there are some high values maybe in the other ones also, sporous high values. So you have the leveling action, grouping the two together and doing the quartile subdivision, you come to this pattern here. Some anomalous and a fewer anomalous values as over there. On C, we have the level data. And the level data actually shows patterns almost close in between, okay, this and this. All right. So one is able to actually, I don't know if this is being followed. This is looking at the ore body here in locality 1 alone. This is considering locality 1 and locality 2, and this is the level data for locality 1 and locality 2. In the case of locality 2, which is this, the same thing is repeated. We are looking now at the surface here, because it's where the sampling was. So this is when that locality is evaluated on its own, you have these patterns here. But when you consider that with locality 1 as well, that is locality 1 and locality 2, most of these anomalies will disappear. That is more a scenario when you are doing an exploration over a terrain and you consider all the data you have together. So you will come to this. When locality 1 and locality 2 are transformed, then you have this anomalies here. So this becomes fairly very similar, to this. So I think this is more like the story which I wanted to tell today. A scenario where you do a sort of a blanket evaluation of data, a scenario where you look at anomalies, separately, which is not done actually, and the other scenario where you do data transformation on groups, well-identified groups in the field. Certainly, there is a difference, in the patterns, that you see. So, in conclusion, I will say that I have tried in this presentation to reinforce the importance of terrain mapping in establishing spatial distribution of regolith units during soil sampling. It's important, I think. It's actually easy to do this in the field because I think the portable XRF is everywhere, almost everywhere for everybody to use now, or increasingly becoming available during exploration. So you actually acquire, using the PXRF, quite a lot of data, multi-element, data, which can be put into use for this purpose. And just go the step further to sort of delineate the regolith units because they play a role in the element dispersion. The appropriate leveling algorithm, can be selected, So, and of course, I would suggest that you follow the steps. Step 1, classify regoliths using XRF data. Maybe use a combination of cluster analysis. It may not be as complex as this. Sometimes it's possible you use simply the discriminant projection analysis straight ahead. I think that can be plugged straight into the XRF, plugged in the sense that the software, I know that EOGAS has the possibility of getting your data arrived from the XRF into the software, and you can even make the plots immediately in the field without wasting of time. So you use that combination or any other combination that one would prefer. And of course, finally, level the data. I think it would pay to do that. Thank you very much. I think that is what I have to present, and stay safe.
Thank you, Prof. Thank you. Oh, go ahead, Craig.
No, I was just going to ask if there are any questions or comments that people would like to express. They can raise their hand. Savisa, do you want to handle this?
That's fine. Are there any questions? Please use the raise hands feature on the participants window pane if you've got any questions for the professor. And then you can unmute your mic. Okay, Joseph, you've got your hand up. Please unmute your mic and then ask your question.
Yeah, thank you, Sfiso. Thank you, Prof Okujeni. I am one of your students, so
okay.
I am pleased to listen to the lecture again live here.
Thank you.
Now, I just make that I can recall from these techniques that you taught us back in honors. So I'm really grateful to see it again. It was a wonderful presentation. Thank you, Prof.
Thank you very much.
All right, thank you, Joseph. Any other questions? Mashudu, go ahead, unmute yourself.
Thank you, Professor and the other delegates. Wonderful presentation indeed. I need to find out if we're working in a mining houses, do you guys open up for consulting services if we don't have like a full knowledge of our own resources that is in the ground? Do we come to the university and get consulting from you guys to help us to analyze what we have on the ground? Or how do you render your services furthermore to the mining houses actually? That's my question.
Okay, twofold. I've always said I'm still at the University of the Western Cape as emeritus professor, and I can run anything I want. I still have a room there, and also I still have a lab there. So we can, as a unit in the department, also do consulting. But also I have, for tax purposes, I have my registered company. It doesn't prevent me from using university facilities. I only have to pay for them. So my email address, I think, is just C Okujeni. Can I just
Prof, can you go to your first slide? I think it was in your title slide, both your TP and your university emails. Just scroll back to those.
Yes. I did not put the email address there. Yes. It's just the website.
Okay.
Right, so it's just C Okujeni at uwc.ac.za. Or you can use DC Okujeni at itp.net. No, CD Okujeni at itp.net. CD Okujeni at uwc.ac.za or CD Okujeni at itp.net. It's the same.
Thank you, Professor.
Okay, Prof, can you repeat? Can you repeat your personal one? I've just typed the UWC one on the chat. That was
CD Okujeni at itp.net.
Okay, .net. Okay, thank you.
Yes. So we are very available. In terms of analysis, we've got no problems. But one of the things that I've always thought about, which is, I know in the gold mining industry, there are a lot of reefs with different characteristics. We could classify these using the discriminant analysis, projection analysis. It's very much used in gold mines as well. When you want to classify, differentiate between rocks which are mineralized from those that are not mineralized. So it has a very versatile, use, and we don't have any problem doing that. So we'll give you what is most productive, what needs to be mined, and the characteristics.
All right. Thanks. Are you happy, Mashudu?
Certainly. Thank you, Professor.
Thanks. Yeah, thanks, Prof. And look, this is the opportune time when everyone's working from home and there's not much field activities to be reinterpreting your geochemical data. We all acknowledge how tricky it can be, whether it's partial leaches or total digestions, but this is the time to reinterpret to get maximum value out of it. Are there any other questions for Prof? Going once, going twice. I think, yeah, everyone understands it better, or they are either confused, Prof. Prof, I didn't ask you early on, but would you be willing to share the presentation on our YouTube channel?
Sure, no problem.
Okay. Okay.
Yes.
So we will share that. We will share that. Thank you very much. And yeah, again, thank you very much for that very interesting talk. Prof, just before closing, we've got a talk on Monday, carrying on with our lockdown lecture series from Lawrence Maynard. That's on Monday at 1. So we are continuing those talks, not in the frequency as we had during level 5 lockdown, but we do have a few during the week. So look out for those. And you can download the Google Calendar for those events, upcoming events, and you can also check out the YouTube channel. Before I close, Craig, Nolene, anything else from you?
Yes,
Yeah.
Nolene, the talk on Monday has unfortunately been postponed, but we have a talk on Wednesday, which is Richard Goldfarb.
Okay, thank you for that, Nolene. Thank you. Any other comments, Craig?
Nothing from me. Thank you very much, everybody. Thank you, Charles, for the presentation.
Thank you.
Yeah, and with that, thanks everyone for joining us again. Thank you again, Prof. We'll
Thank you.
chat in the next one. Enjoy your weekend.
Thank
Ciao.
you. Yeah, okay, you too.
Thanks,
Cheers.
bye.
Bye-bye.